Okay, so moving on today, we're going to be looking at regression. Now, regression is a follow-on and a more specific version of a line of best fit. So the regression line is going to be the A-level version, the further maths version of your GCSE line of best fit. The way that you used to produce a line of best fit was really by eye, and you will just try to produce a line that roughly went through the points that you're working with, showed the direction that they tended to move in, and a rule of thumb was to try and get the same amount on each side. So there were many lines of best fit that might have been acceptable. This looks like a decent line of best fit and would have got you marks on the GCSE exam, or I could move it a little bit. This may well have been a good line of best fit, but anything too far away wouldn't have counted. Technically, what we're doing is we're measuring the distance of each of our points from the line that we've produced. And you can see as we move the line, these residuals, the distances here are called residuals, these residuals can take larger values. To get the best line of best fit, the most appropriate regression line, we try to minimize those residuals. We could see that also as squares. We're trying to get the smallest square area. The squares are each a representation of how far away our points are from the regression line we're anticipating using. The best regression line is called the least square regression line. It's the regression line that will produce the least area to the squares made by the residuals. Here's the actual regression line in purple, the most optimal regression line. So I wasn't too far off, but obviously at A level and in further maths, we want to be quite and very specific. So we're going to be working on how to calculate, how to establish that least squares regression line. Here are some summary statistics we're going to need to use and get familiar with. The S of XX, S of YY, and the S of XY. Now, each of these summary statistics is a type of variance. It measures how the values vary within that variable. So the S of XX is a measure of the spread of the X values. You might recognize S of XX as it used to be part, or it was always part, of our variance formula. It was the numerator. The S of XX over N equaled our variance. If we make S of XX the subject by multiplying through by N, we get two different descriptors for S of XX. One from the original variance formula and one from the alternate variance formula. So multiplying through by N, S of XX equals the sum of X squared minus the sum of X squared over N. And you can see similar themes for S of YY and S of XY. So just so you know where these summary statistics have come from, they've not just been plucked out of thin air. It is a measure of the spread, the variance, the variation of either the X value, the Y value, or a combination of the X and Y value. Okay, so there's two more things I've put on the screen here. You can see to calculate A, we're going to use Y bar minus B X bar, and to calculate B, it's a combination, a ratio of these two summary statistics, S of XY over S of XX. The actual equation for our regression line is going to be Y equals A plus BX. As long as we can find A and we can find B, we can find the equation of our regression line. Okay, so let's try an example. Here we have some data that's been collected from adding a mass to the end of a string and seeing how far the string expanded. We're asked to find S of XX and S of YY using the summary statistics given. So really it's about recalling the formula, sum of X squared minus sum of X squared over N, and substituting. so we get 4,000. Formula, sum of xy minus sum of x, sum of y, over n. Substitute in, we get 922. Part B has asked us to find the regression line. So this is where we have to find B, and we have to find A, and we'll put it all together to get the regression line. So B is going to be 0.2305, and as usual, I'm going to stick to 4 decimal places where I can. A is going to be y bar minus B x bar. I'm going to use the same B value, as in the exact value, the fraction that I was working with before. And we get that A equals 43.89. Okay, let's put this all together. Our regression equation, y equals A plus bx. So y equals 43.89 plus 0.2305x. Next, we're asked to make a prediction about the length of the spring when the mass applied is 58 or 130. We're just going to substitute this into our regression equation. So, substituting 58 gives us 57.259, and substituting the 130 gives us 73.855. Finally, part D just asks us to talk about the reliability of each of those predictions. Now, just like we saw in straight maths, if we make a prediction within the original data, it's reliable, and that's interpolation. Anything outside of the original data, 130 was bigger than any of the original data points. This is extrapolation. Extrapolation is dangerous. Extrapolation is unreliable. We do not like to extrapolate. So 58 is reliable, 130 not so much. Okay, let's have a look at another case which will be slightly trickier. Here we have some data about the amount of food supplement given to some chickens and the hardness of the eggs that they lay. Here, if you notice, we're not using x and y as we usually would, but we have different variable names. So just be on the lookout for that, and don't let it throw you off. We've been asked to find the equation of the regression line of h on f. We've not been given much to go on. We've just been told that, and we need to do all of the preceding steps ourselves. So usually we'll start with s of xx, and we just need to swap that out for the variable which matches x, which in this case is going to be f. So the s of ff, substitute in summary statistics, we get 112. We'll do a similar thing for s of fh, substitute in all the correct values, we get 56.2. Okay, from here we can go ahead and we can calculate B. B is always going to be the combination of two variables in the summary statistics. So S of FH is going to be the numerator, and then we're going to double up in the denominator, so that will be the S of FF. Okay, substitute, and we get 0.5018. Okay, we've got B. Let's go ahead and find A. So y bar is going to be h bar, and x bar translates to f bar. Substitute in those values, 2.5287. The equation of the regression line, just make sure we're using the correct variables. H equals a plus bf. We'll substitute the a value we found and substitute the b value that we found. So, the equation of the regression line. We're asked to interpret what the values a and b tell us. Well, a, I'll call the vertical intercept rather than the y-intercept, since the vertical variable, the dependent variable, isn't even y. It's the vertical intercept, and as always, this tells us the value of that variable when the independent variable is 0. So in this case, the hardness of the eggshells when the amount of supplements added is 0. What about b? Well, b is the gradient, And just as usual, the gradient tells us how much we should expect the dependent variable to increase for every unit increase of the independent variable. In this case, it's the expected increase in shell hardness for every extra unit of supplement used. So, being able to generate the equation and obviously interpret an equation in terms of its intercept and its gradient as we usually would. Okay, we'll just do one more example and I'll try and go through this quickly. The first two parts are just like you would expect. We're calculating the summary statistics, so we're going to substitute the information that we've been given already. So this time around, S of xy, we're going to get 6.776. And we've also been asked to find S of xx. And if we substitute our values, we get 6.72. Part B of the question, as you might expect, we're asked to go ahead and find an equation for our regression line. So we're going to calculate B, we're going to calculate A, and we're going to substitute them into the usual form for the equation. So when you're actually asked to draw a scatter graph, your calculators are powerful enough to be able to do this for you. So as usual, we would want to go to our statistics menu and we have the opportunity to input some data here. We're going to input data for list 1 and data for list 2. We'll put our x values in list 1 and our y values in list 2. Our independent values in list 1 and our dependent values in list 2. Okay, so from there, instead of pressing F2 for calc, as we're used to doing, we can go ahead and press F1. F1 takes you into the graph menu. You have a choice of a few graphs, but usually graph 1 would work well. So just hit F1 again for graph 1. And there we go. We've got our data points on a scatter graph ready to give us an understanding of what type of correlation or regression we have. We have a visual that helps us to decipher the raw data we started with. Part D then asks us to find out what the reading should be if we got a gauge reading of 2 bars. So this is just a contextual way of us being asked what would be the output if we had an input value of 2. Using the regression line, what's the value of y when x equals 2? So being able to decipher that context is quite important. Okay, so this is just a technique that you're going to need to practice and really get used to. These summary statistics are going to come up in more than just this calculation of the least squares regression line. We're going to see them come up in correlation and a few other topics down the line. So get some practice on these and we'll be back to take these summary statistics further.